Good morning all. It is still summer, it's August the 10th, although it's hard to believe with 2 inches of rain yesterday and condensation on the windows this morning. I had to turn the central heating on today. But we press on because I'm still working on the summer project, which is to build something like this. It's an 8-cell or up to 8 cells monitor that can monitor the voltage on a lithium pack, and this is also a discharger so that this can discharge and balance the cells in that pack. So today I want to play with this. It's the Secret Voltmeter. This is on Google Code Archive, and I'll provide a link to this page in the description beneath the video. So what this does is it's a piece of code that allows the Arduino, using an ATmega328, to measure its own voltage rail, to measure VDD or VCC. So let's cut this code section out here, paste it into Arduino, download it to that Arduino Uno, and see if it works. Right, so here's a new sketch for today, August the 10th, and let's paste in there, Control V, that code I got from the Secret Voltmeter page. I don't quite know why they've written the first line as one great big long line, which runs over about 3 widths of the screen. I might try and put that on separate lines a bit later, but just for the moment, let's see if that runs as it stands. So just saw there's a space there which I could take out. The other thing is a couple of people were saying, can we have bigger text? So I've increased it from 12, I don't know, point is it, to 18. So it's bigger now. So let's see if that will compile and upload. Right, well, this is a classic, isn't it? This won't compile. It says a function definition is not allowed here before bracket token, whatever that means. Right, well, I've moved a couple of these bracket things down, but that doesn't seem to help. So I think what I'm going to have to do is take this big long single line and break it up into separate lines. But it's not actually easy to see where lines begin and end, because here we've got long result, there's the semicolon, then there's a comment. So I think the next line starts there, AVCC, oh no, read 1.1 volt reference against AVCC, so it starts there, addmux equals, so let's bring that onto a new line. So addmux equals these registers all ORed together, then there's a delay too, that can be another line. That's got a comment, wait for vref to settle, then there's another register here, so that must be the beginning of the next line. I'll keep going, bringing these lines onto separate lines and see if I can piece this thing together and get rid of this compilation error. Okay, so I've chopped this up into separate lines. It does seem to compile now, so now I'm going to do a compile and upload. That compile shouldn't take long because it's already done it. Let's see what the Arduino does. Right, well, not an awful lot, although I can see there that the RX LED is briefly flashing once per second. If I look at the code, there is a delay 1000 in there. So I think what it's doing is it's writing a value back to the serial monitor. So we'll need to open the serial monitor and see what's coming back from that. And here's the serial monitor. And yes, we're getting this number coming back, 5073. It is scrolling down the screen, but it's not changing at all. Now, it did say on the Secret Voltmeter page, well, actually, let's have a look at it. Oh, it has just changed, look. 5073 and 5096. Let's go back to that page. Yeah, so it says here, the voltage is returned in millivolts. So 5000 is 5 volts, 3300 is 3.3 volts. So looking back at the results coming back from the board, what we have here appears to be 5.073 volts, or 5073 millivolts, and that's just flicking up to 5096. Now this is not very useful, and I can't actually vary VCC because I can't vary the voltage coming out of my PC, but it does tell me something, and that is we're going from 73 to 96, so that's 23 millivolts of resolution, because that's going to be one analog to digital conversion bit change. And that's fairly coarse, isn't it? 23 millivolts of resolution. I'm not sure that's going to be fine enough to measure the voltage of a lithium cell, for example. So what I really want to do here is power this from a voltage less than 5 volts, but then send that voltage information, well, somewhere. At the moment it's going back over the USB to my PC, but of course if that cable is plugged in, I can't have less than 5 volts on this board. So I think I'm going to have to bring in my old friend the OLED and this Arduino Pro Mini. This ammeter, this INA219, won't be used. But what I can do here is install the code in here and also add in some code to drive the OLED so that we can see that millivolt value on there. Then I can power this with less than 5 volts and see if that display responds to the voltage change. So what I need to do here is open my other sketch, which is this one, my OLED and INA219. Let's open that. And I'm just going to have to sort of chop bits out of here that I feel that I need to get both the reading of the VCC voltage and then writing that to the OLED display. So I'll start doing that now. What I'm going to need is wire for the I2C, Arduino H probably, U8 glib. I don't need INA219. I don't think I need SPI. So let's take those bits. I'm also going to need this U8G2 constructor call here, and also the U8G2 begin. So let's grab those two bits. And I'm also going to need the stuff which actually writes to the display. So clear buffer, set font, set the cursor, then print a value. And what I'll do is, instead of this print line read VCC, I'll do a U8G2 print read VCC. I've already got a delay, so I don't need that. Yeah, let's cut those bits out. Right, so I think that's everything. I'm doing the read of the VDD, and then I'm sending that out to that little OLED. Now I need, of course, to change this from an Arduino Uno to a Pro Mini. Okay, so that's all done. Compile and upload, and let's see what the result of that is. And the result of that is this, which is encouraging. We've got that same number, so that's almost exactly 5 volts, but this is jumping around a bit more. 5006 and was it 5028 I saw? Yeah. So that's 22 millivolts of resolution. I think we had 23 before, so that's similar. Now 5006, what would be the one under that? 4984. So 4984 up to 6. Again, yes, that's 22 millivolts of resolution. So that's working the same. What I want to do now is see whether this number here tracks the voltage if I wind the voltage down. So I'm actually going to power this now through the raw input. Now that does go through the voltage regulator, but I'm going to drop the voltage down below the regulator's regulation voltage, and so it will probably just not do anything, maybe just act as a diode volt drop, possibly a semiconductor volt drop. And just see whether this number drops as VCC drops. So let's find a little power supply. Right, so I'm going to use this little power supply. This is the Minghe B3603, so up to 36 volts out. Of course, it's only a buck, so you'd have to put 38 volts or something in, up to 3 amps. So what have we got? We've got 5 volts. What's it set to? Current, 100 milliamps. That's a bit low. Let's give it Arduino-y sort of current. Let's give it half an amp. Save that. So we've got 5 volts and half an amp. Now I'm going to connect the little display, and I shall need a piece of wire with a suitable plug on, so I'll use that. Right, let's put the negative in, the negative out. Has that gone in properly? Need to clamp that down on there. Yeah, seems all right. Positive into positive out. And then the big switch on. Will it work? Of course, there may be quite a lot of noise coming out of this power supply, but then I suppose the 5-volt PSU in a PC is also switch mode. So, okay, so 5 volts switch on. Right, yes, that would be right because we've got 494. Yeah, we've got almost 0.6 of a volt of drop. So I suppose that's happening in the voltage regulator. Now the interesting thing is when I wind this down, so let's come down to 3.7. Yeah, we got 3.6 there. So yes, that bit of code is actually measuring VDD. Let's come down to about 3 volts, 2.8. Let's come down a bit further. Oh, that has gone very dim and it seems to have locked up. Now that's probably because at 2 volts this display isn't going to function. I wonder if I take that back up, whether that'll burst back into life. Let's go up to 2.5 volts. Well, it's brighter, but it's still saying 2727. Let's go up to 2.7 volts. No, still not working. 2.8 volts. Ah, right, that's come back to life now. So at 2.8 volts, the OLED is working. I'm pretty sure the microcontroller can run at a lower voltage than this. So it's probably the OLED that's packing up at this low voltage. But yeah, that's tracking reasonably well. That's saying 2.74. So again, a 0.6 volt drop from 2.8, assuming all these voltages are accurate. So certainly that seems to be tracking VDD reasonably well. Now, what's the millivolt resolution here? Well, it looks like it's 33 to 40, which is much better because that's only 7 millivolts of resolution, whereas up at 5 volts we were getting, what was it, 22 millivolts of resolution. So the resolution certainly seems to be better at the low voltage end. So how is this Arduino Pro Mini, able to measure its own VCC? And that's the only thing connected to this Arduino. It's just these 2 wires, and it's actually measuring the value of VCC. How is it able to do that? Well, I've printed out a couple of pages from the ATmega 328p datasheet, and this is the section on the analog to digital converter. So the way the analog to digital converter works is that you have a comparator here and a digital to analog converter. So what you do is you put different values on the digital to analog converter and you find the point using a process called successive approximation. I'm not going to go into that here, but I will put a link to a video I did on how A to D converters work previously, so you can view that. But you find the point at which this comparator is just flipping from one state to the other, and that means that the output of the digital to analog converter is the same as your analog value coming in on one of the 8 analog pins, A0 to A7. Now the point is, the digital to analog converter works a bit like a potentiometer. It gives you on its output a proportion of the voltage on its input, and that proportion is simply the binary number that you put in relative to the maximum binary number, which is 1024. We'll use 1024 because that makes the maths correct. 1023 is the actual maximum number you can put in here. So if you put in 1023, then you get pretty much the full value of voltage that's being fed into the DAC. You'll get it coming out of here. And if your analog input is also the maximum value of voltage, let's say 5 volts, then that's where you'll get a comparison on the comparator, and you'll know that 1023 is the equivalent of the voltage coming in on your analog input. But that assumes that we've got 5 volts, which is here, AVCC, routed through to the DAC. Now this measuring own VCC program uses a different routing. What it does is it talks to these registers up here and rearranges, instead of VCC being on the DAC, so instead of the DAC having the full 5 volts and its output being a proportion of that 5 volts dictated by the binary number that you put in, we actually feed a different value into the DAC. We actually feed in What do we feed in? We feed in VCC. Actually, that's not changed. It still routes VCC in, but of course here, VCC is now only 2.8 volts. So the output of the DAC is a proportion of that currently 2.8 volts, dictated by the binary value that you're putting in here. If we put in the full 1023 binary value, then you'll get 2.8 volts coming out of here. So what do we put into the analog input? Well, we actually put in this thing, the band gap reference. And although it's got a different name, band gap reference and internal 1.1 volt reference, it's actually the same thing. It's just that up here it's buffered. But this is a fixed 1.1 volt analog input. So if we had a fixed 5 volts on the DAC, then this would always measure 1.1 volts, or at least the binary equivalent of 1.1 volts. But because we've now got a varying VDD or VCC, currently down to 2.8 volts, but I can take that up to 5 volts, we've got 1.1 volts as a proportion of this varying amount. And this means that our mathematics is all upside down. Normally we've got a fixed 5 volts driving the DAC, and we've got a varying analog input varying between 0 and 5 volts, providing different analog or binary values. This is the other way around. We've got a varying VDD and we've got a fixed 1.1 volts as our analog input. So the maths is actually flipped, it's inverted, and you can see that from the code that makes this thing work. Right, so here it is. I've printed it out in the new larger font size, so I'll just bring the camera out ever so slightly. The first section here is what adjusts the registers, this register mainly up here, to reroute, well, it's the one that selects, it's this section here, this decoder, that selects which of these inputs is fed through to the analog to digital converter. Now normally you'd select either A0 to A7. Here we're selecting the band gap reference. So that's done with this first statement. Then we do an actual analog to digital conversion. We read the result in, and here we take a fixed value. This is a long, but it's a fixed value, and divide it by the result. So we're taking the analog to digital conversion result and putting it on the bottom of a division with a fixed constant on the top. That's this flipped over thing I was talking about to calculate the voltage in millivolts. Now normally when you use the analog to digital converter the right way round, with 5 volts driving the DAC and a variable voltage on the analog input between 0 and 5 volts, the resolution is about 5 millivolts because you've got a 10-bit DAC, so you've got about 1,000 different binary values. It's actually 1,024, so the resolution's slightly better than 5 millivolts, but that's over 5 volts. So that gives you that 5 millivolts. But here, because this thing's flipped upside down, we've got a variable resolution. It's not bad down at the low voltage end. In fact, if we could get this voltage right down to 1.1 volts, we'd have the full 5 millivolts of resolution. But even at this 2.8 volts, we're getting 7 millivolts of resolution, 33 to 40. It's only when we take this up to 5 volts, and I'll do that now. Let's whiz that up to 5 volts. 5 volts. We're now getting, I think it was 22 millivolts of resolution. So the resolution is much less good when we're a long distance away from the band gap voltage, which is 1.1 volts. We're getting much poorer resolution. Now the question is, for my project, is 7 millivolts, was it, of resolution deteriorating to about 22 millivolts of resolution, although of course lithium cells don't go up to 5 volts, so we might call it, I don't know, maybe 15 millivolts of resolution. Is that enough for building something like this, the cell meter, for measuring lithium cells? Let's just plug a lithium pack into here and see what resolution this operates at. Let's take a look at the cell voltages, and you can see that it's sort of oscillating between 3.801 and 3.800. So this ostensibly is measuring to a 1 millivolt resolution. Is between 7 and 15 millivolts going to be enough? Or does each of my Arduinos, and I am planning to have 8 of these Arduinos, one measuring the voltage on each of up to 8 cells. Do these Arduinos need some sort of external chip to do a more precise voltage measurement, or can I get away with this built-in secret voltmeter? Is it good enough? I shall have to have a think about that, but for the moment I just wanted to see this in action, and it does seem to work. Let's just drop that voltage down again. Let's go down to about 3 volts, near enough. Yeah, this does seem to measure its own VDD, so from the point of view of just seeing this working, well, I'm quite happy. Cheerio.